What if there was a telescope so powerful it could give us a whole new picture of the cosmos and help us answer some of the biggest questions about the universe and life itself? Hello, you're listening to Where What If Becomes What's Next from Carnegie Mellon University, where we ask the bold questions that become innovations for the betterment of humanity. I'm your host, Randy Scott, and in this episode, we're taking you farther into the stars than we've ever gone before. On June 23, 2025, humanity opened its most powerful eye to the cosmos. High atop a mountain in the Chilean Andes, the Vera C. Rubin Observatory released its first images of the night sky. And with them, a flood of light that had been traveling across the universe for perhaps billions of years finally reached us. Every 3 nights, the Rubin Observatory's telescope, the most powerful in the world, is essentially making a movie of the entire night sky by capturing data from more than 40 billion stars, galaxies, and asteroids. In those inaugural images, millions of distant stars blazed across our screens, entire galaxies revealed their spiral arms in stunning detail, and thousands of new asteroids emerged amid the cosmic darkness. The Virgo cluster, that magnificent collection of over 1,000 galaxies located 50 million light-years away, appeared with a clarity and scope never before achieved. And these first images are just the beginning. What we witnessed that day was the dawn of the most ambitious astronomical survey in human history, called the Legacy Survey of Space and Time, or LSST for short. The LSST will be a decade-long quest to map the universe. The Rubin Observatory isn't just another telescope. It's also a time machine capable of capturing the faintest whispers of light from astronomical events which happened billions of years ago, such as the explosive deaths of distant stars, known as supernovae, and the movement of asteroids. Over the next 10 years, this revolutionary instrument will capture more astronomical data than all previous surveys combined, promising to fundamentally transform our understanding of the universe and reality itself. We first reported on the Rubin Observatory before the telescope came online and started producing these amazing images in our podcast's first season in the episode Stellar Observations: AI's Journey into the Cosmos. In today's episode, we're going to take you behind the scenes where scientists and researchers at CMU's McWilliams Center for Cosmology and Astrophysics have been creating the software, algorithms, and computer tools necessary to help turn the observatory's massive collection of data into visual images, meaningful data, and scientific breakthroughs. But first, let's look under the hood. Located on a mountaintop in Chile, where atmospheric interference is minimal, the Rubin telescope has revolutionary technology. It has a one-of-a-kind 2-in-1 28-foot mirror, which took 7 years to build. The mirrors funnel light from the night sky into the world's largest digital camera, which itself is about the size of a small car. The camera has an amazing 3,200 megapixel sensor. By comparison, the high-powered camera on an iPhone 16 has a mere 48 megapixels. The Rubin's camera is so powerful it can spot a golf ball from 15 miles away. As the Rubin telescope captures images of the night sky every 40 seconds, it is generating massive amounts of data, 20 terabytes of data every day. It would take you over 3 years of watching Netflix or over 50 years of listening to Spotify to use that amount of data generated in just 1 day. The data is housed at data centers around the world, which can be accessed by scientists through their computer browsers using the Rubin Science platform. This online portal provides a simple user interface and tools that allow scientists to access and filter the data according to their specific areas of interest. But making sense of this data, that's another story. In fact, without the next generation of computational software, many, if not most, of the Rubin's observations would remain unseen. The real power of the telescope isn't just in its mirrors and super camera. It's what happens to the data after the light is collected. And that's where the scientists and researchers at Carnegie Mellon come in, through a multi-year project called LINCC Frameworks, which stands for LSST Interdisciplinary Network for Collaboration and Computing. We sat down with Professor Rachel Mandelbaum, who is the interim head of Carnegie Mellon's Department of Physics and CMU's lead for the LINCC initiative, and Jeremy Kubica, the Director of Engineering for the LINCC Frameworks. Rachel, Jeremy, can you give us just a little background on the LINCC Frameworks?
CMU has partnered with the University of Washington to establish a project called LINCC Frameworks. And the goal of LINCC Frameworks is essentially to develop software infrastructure that can be used by the entire LSST science community to more effectively analyze the very large data sets that will come from LSST.
The challenge will be the volume of this data is going to be so difficult for astronomers to process just based on the size of the data. I mean, you mentioned 20 terabytes a night, and that's accumulating night after night. So what my team does, the LINCC Frameworks team, is we are actually designing software that is trying to be scalable with respect to analyzing the data once it has been collected by the Rubin Observatory. We start from where the Rubin Observatory's data processing ends. The Rubin Observatory is going to produce this wonderful set of data that's both catalog images of where objects are and measurements on them, and also actual raw images as well.
Now, the LINCC Frameworks project started about 3 years ago. And Jeremy, you were the first person hired. So what was the first thing you did to begin development of the software?
We had a workshop right before I officially joined called Data to Software to Science, which brought together a bunch of astronomers and said, what are going to be the major science things that you want to do on the data coming off of Rubin? And then what are the computational challenges that you're going to face while trying to do this science? And we assembled a massive list of things that we thought were going to be computational bottlenecks. And my team's mission is to solve as many of those as possible.
Which probably led to a lot of software innovations. One of those is access. Now, Rachel, who will have access to the software the team is creating, as well as the data and images from the LSST initiative?
The way that this project works is that the US and Chilean scientific communities have access to the data right away, along with many other international communities that have joined as partners. So, there are communities in the UK, France, Germany, many, many other countries that will have access to the data. And the software that our team is producing is fully open source. So anybody, even while we're developing the software and still working on it, anybody has access to it, whether or not they have access to LSST data. And then after some period of time, the data become, 100% public to the world. But our hope is that the communities that have the direct access to the data early on will make use of our tools right away, because as soon as they do that, they're going to get to do their science, but we're going to also learn, where are the areas that we can improve. And we hope to kind of iteratively improve the software as the community makes use of it and learns about how is it working well and where could it stand to be improved.
Okay, now, Jeremy, what does open source mean for the scientific community?
Everything that LINCC Frameworks is doing is open source. It's available for the most part on GitHub. The goal is to have the entire astronomy community benefit. The focus of the team is enabling science on Rubin, but nothing we're developing, or very little that we're developing, is specific to Rubin. The work we're doing on catalog storage formats will apply not only to data coming from Rubin, but from space-based telescopes as well. So the hope really here is that we have a pretty broad impact on science overall.
Okay, and that aligns with a broader philosophy of open science, right?
Correct. Yes. Really trying to be very collaborative and to make sure that everybody can benefit from the software we're writing.
Including smaller universities that may not have the resources for this kind of research, right?
Yes. The open source aspect of all the software, I hope, gives a chance both for the smaller universities to use the software and to benefit from it, to be able to run analyses that they might not have previously been able to, but also to contribute back to it if they want and to help kind of shape the direction. We're trying to be incredibly collaborative and really make sure that we benefit from community input as well.
Great. Now, the LSST will generate trillions of observations that scientists will want to analyze for their own specific research. But previous ways of working, such as downloading the data and analyzing it locally on your computer, just won't be feasible. One of the innovations in making the data accessible to scientists around the world was figuring out a new way to bring the scientists to the data and not the data to the scientists.
Our mission is to write software that takes the data products that are being produced by the Rubin data management pipeline and enables analysis of those. So a good example of this is Rubin is producing catalogs of data. And these are basically tables with object information, including measurement information of like brightnesses and all sorts of derived information. One of the things my group is working on is a framework to take this catalog data and process it very efficiently in a distributed fashion. So over many computers. So that way, if you want to run an analysis of time series, you're able to do that in a scalable way, which you might not be able to do if you're trying to run this all on a single computer.
So impressive. Now, scalable open source software distributed across a network of computers, giving access to and fostering collaboration among scientists around the world. Now, this seems like a good place to take a quick break, and when we come back, we'll explore more data and computational innovations that are powering the Vera Rubin Observatory. We'll also take a look at what's next for the LSST project and how you can get involved.
This podcast is brought to you by Carnegie Mellon University. Located in Pittsburgh, Pennsylvania, CMU is a private, international research university, consistently ranked among the top universities in the world. Its trailblazing research is focused on creating, defining, and accelerating the future of artificial intelligence. For more information, please visit ai.cmu.edu.
Welcome back. You're listening to Where What If Becomes What's Next from Carnegie Mellon University. We're talking with Professor Rachel Mandelbaum and Jeremy Kubica from Carnegie Mellon University, who have helped develop the computational brain behind the telescope at the Vera Rubin Observatory in Chile. So how else is your software helping scientists to see things from the data they wouldn't otherwise see?
We have this one project called KB-MOD, which is trying to take images and find moving objects that are too faint to find with a single image. So the goal here is really to find TNOs, trans-Neptunian objects that are out so far in the solar system we can barely see them. But if we take a bunch of images and we shift them all to align them correctly and stack them on top of each other to account for the motion, then all of a sudden we see these objects appear where we couldn't see them in an individual image. So in that case, we're taking the images and what we're producing is actual knowledge about physical phenomena. Like there is an object out here with this orbit, which will allow us to then answer a whole bunch of interesting questions about how the solar system formed.
And I also understand that another way you've collaborated with scientists and researchers to develop innovations for the Rubin telescope was through incubators. Jeremy, can you tell us a little more about that?
Yeah, I can do that. One of the innovative aspects of the LINCC Frameworks team that we've really been enjoying and seeing an impact on is a program called incubators. And those are 3-month intensive collaborations that we have with members of the scientific community. So generally people who have analyses that aren't scaling or they would like to try something new or implement something new. We have a 3-month period where we collaborate very closely with them, go very deep on their problems and try to solve them and produce useful software for the entire community. And we run these 3 times a year. There's a selection process for people to submit applications to work with us. And the nice thing is we've really gotten to address a range of problems within the analysis phase of the Rubin data stream. So it's a lot of really cool work has come out of that.
And Rachel, you've been working on a project that actually predates the LINCC Frameworks initiative. So developing computer algorithms that help us to see the accurate shape of galaxies without interference from other heavenly bodies or Earth's own atmosphere. Can you tell us more about that?
One thing I've worked on that I'm particularly proud of is algorithms for measuring coherent patterns in galaxy shapes. And so you might ask, well, why do we care about that? So there's this effect called gravitational lensing, where light from very distant galaxies passes by massive objects, and the light rays get slightly deflected in their paths through space-time. Essentially, any galaxy that we see in the universe has been gravitationally lensed. It affects all of them. So it's a great way to learn about the distribution of mass, including dark matter in the universe. The thing about it is we don't know what the galaxies looked like before they were gravitationally lensed. So we have to measure gravitational lensing by looking for coherent patterns that the effect introduces into the light profiles of the galaxies, like their shapes become slightly correlated. And this turns out to be a challenging thing to measure because there are other physical effects that are much less interesting that can cause the same effect. For example, when light rays from distant galaxies pass through the Earth's atmosphere, they get distorted in ways that can also correlate their shapes. But that's not what we're trying to measure, and that's not particularly interesting. So I've worked on two different algorithms that are kind of the leading candidates for use by Rubin Observatory LSST to measure weak gravitational lensing. And this is something that is one of the major cosmological applications of that data. And so I'm very excited about that.
I'm sure you are. That does sound very exciting, Rachel. Jeremy, what's on the horizon for you and your team?
I think what's exciting is we're really at the starting point now. Once the data comes in, all of a sudden, we're going to see new challenges that we didn't even expect. So new questions are going to come up, and we don't even know what analyses people are going to want to run or the questions they're going to want to ask yet. So we think that there is a huge amount of potential impact that we can still have that we don't even know what people are going to need until they start looking at the data and saying, wait, this looks weird. What if I looked at it this way? And we need to introduce new analysis. So very exciting time for us.
So as we wrap up, we've learned how Rubin's 10-year movie of the cosmos will bring the night sky to life, yielding a treasure chest of new discoveries, most we can't even predict yet. But we do know that this revolutionary telescope, coupled with the computational innovations from the LINCC Framework initiative, will help us to better understand the universe and how we on planet Earth got here. It will help us understand the nature of dark matter, the mysterious, unseeable parts of the universe that make up 80% of the cosmos, and perhaps hold the answer to how the universe was formed and how it's expanding. It will create an inventory of what's in our solar system, the millions of asteroids and comets and near-Earth objects that is our solar system's history. It's going to map billions of stars and galaxies with unprecedented detail, and it will reveal our dynamic, ever-changing universe, capturing images of supernovae, asteroids, variable stars, and unexpected events. Equally important, the observatory and the LINCC Framework initiative will perhaps reshape discovery itself, using innovative open-source software to foster unprecedented collaboration among institutions big and small, research facilities, scientists, and citizens around the world. Let's fast forward 10 years to when the LSST mission is completed. Jeremy, what do you hope to see?
I hope we answer questions as into the nature of dark matter and the nature of dark energy and the formation of the universe and the formation of the solar system. There's so many potential big questions that we can get insights into. I'm hoping that looking back in 10 years, astronomers will be able to say, I was able to make this discovery because of this software.
That would be quite a legacy. Rachel, how about you? What do you hope to see?
What if the data from Rubin Observatory were used to discover another planet in our solar system and asteroids that we previously didn't know about? What if we could build software that would enable astronomers to access and run their analyses on the billions of objects that will be measured by LSST? What if we could understand how the solar system formed and evolved, and we'd just be driving rewrites to the textbooks?
Well, that'll do it for this episode. We want to say a special thank you to our guests, Rachel Mandelbaum and Jeremy Kubica, and a big thank you to you for listening. If you'd like to be involved in the Rubin Observatory's 10-year mission, you can visit their website and explore the first images from the telescope, watch slideshows on the observatory's technology, or even join a research project as a volunteer citizen scientist. There are countless ways to get involved. Please check the show notes where you'll find links to additional resources for this episode. And if you want to learn more or contact us with a story idea or comments, go to cmu.edu/What's Next podcast. If you are enjoying this show, please rate and review us on your favorite podcast site and share with friends. Don't forget to subscribe so you'll never miss an episode. I'm Randy Scott, and you've been listening to Where What If Becomes What's Next from Carnegie Mellon University, where we are asking the bold questions that become innovations for the betterment of humanity. Stay tuned and stay curious.